Okay, there's still a couple of people missing, but I think in the interests of keeping going and getting through and getting people doing stuff and not having people sitting down doing nothing, we'll just get started and they can catch up once they're back. So I'll kill that poll so it's not in our way anymore, so I can see what's going on. So we had a look at the context in the last session about where the HPC use fits in the sort of wider HPC workflow. A very brief look at that. I mean, that whole workflow and optimizing your workflow and understanding your workflow really could be a whole course in itself. But because this course is more focused on the HPC side, we're going to move on to look at the specifics of the HPC part of the workflow now. So in this session, we're going to have a look at benchmarking and what benchmarking means and some of the key terms behind that, so we have an understanding of what we're talking about and the terms we're using when we're describing things throughout the course. We'll have a look at what performance metrics are and what parameters can affect the performance of an application. And this reflects the main tool we're going to use throughout the rest of this workshop is benchmarking, or at least these basic benchmarking to try and understand the performance of our application or our HPC use, and then crucially turn that into something that we could use to inform decisions about how we use our HPC resources. So first of all, I want to give both a brief intro to benchmarking, why it might be useful, terminology, and then we'll get started with actually running some stuff on Archer 2 itself. So benchmarking, hopefully, I mean, most people have a sense, I think, of what benchmarking is, but sort of formally, it's measuring how the performance of something, in this case, our application, varies as we change various parameters. So in this case, we're benchmarking parallel software and HPC systems, and the parameters we measure performance variation against usually either one of or a combination of the number of parallel MPI processes, often MPI processes we use, the number of threads, these are often OpenMP threads in HPC land we use, the distribution of those processes and threads across compute nodes, any scheduler-specific options that affect performance, so that's usually linked to process or thread distribution, or for example, the use of physical or logical cores on a compute node, and also potentially calculation input parameters that can affect performance. Now, the thing that's not on here, which potentially people might want to look at as well, which we're not going to really cover in this course because our Archer 2 is very homogeneous, is that you would maybe also look to understand the performance on different types of systems. So you may have access to multiple HPC systems and want to know which of your research cases fits best on each of those different HPC systems. So one might have some GPU acceleration, one might use Intel CPUs, one might use AMD CPUs, ARM CPUs, whatever, or have different interconnect types, different storage types, and those sorts of things. And so you can also use benchmarking to compare performance across different hardware and architecture types as well. But in this case, for this course anyway, at least, we're going to be exclusively using Archer 2, and all the compute nodes are the same. So actually, in our case, we're really going to be looking at how performance varies with power with different numbers of cores. Okay. Why would we use benchmarking? So the first case here is essentially what we're going to look at particularly today is understanding how your current calculations scale to different node or core counts to choose the most appropriate setup for your work. So what we're going to do today, or what we're going to work through today, is running our application at various core counts, analyzing the performance differences, and turning that into something that we can make decisions about what's the best choice and what are the trade-offs we're making in terms of core count choice versus resource usage on a system. And that's often what a useful thing to do when you first get access to a new system. Say you've just been given access to some resources on Archer 2 for the first time. You have some calculations or some use you want to make of the system. Then one of the things you might want to do then is understand what's the right node or core count to choose for my application, which provides me with a good balance of time to solution versus efficient use of resources. And often you can use some very simple benchmarking, the techniques we're going to talk about today, when you first get on a system to try and understand that and make that make that decision. Because I think quite often, certainly in our experience, what often happens with people when they first get access to the system, especially if they're quite new to using HPC, is they get given a job submission script by somebody else in their research group or handed down a job submission script. And because people maybe are scared to change it in case it changes the results or does something wrong or something like that, they tend not to vary the parameters in very much. And what happens is that this script then gets passed down throughout the research group for a long time, and it doesn't vary very much, when potentially people could be making much more efficient use of the resources if they could explore the performance a bit more. And I'm not talking about doing like some sort of very extensive benchmarking exercise here. I'm talking about running maybe 3 different node counts. I mean, typical one we often advise people to use is, if you've got a job submission script, you've been using a certain core or node count, double it and halve it and try it again and see what the performance variation is in the first instance, and that should give you some pointers as to whether you're being efficient or not. Okay, but another use for benchmarking in terms of what we're talking about here anyway as well, it would be understanding how much resources you need to ask for in a future say grant application or a request for resources on an HPC system. How do you estimate how much you're going to need to complete that next part of your research program? And simple benchmarking can give you the answers to that. The third thing, which we're not going to talk much about, is benchmark is really commonly used in purchasing new HPC systems to make sure the new system is the right level of performance for the users. So typically there'll be a set of benchmarks, some of them synthetic, some of them based on applications, and based on the performance of those, people will score different vendors of HPC systems and then choose the one that gives them the best performance for the money, depending on what parameters they're interested in. However, we thought it was unlikely that people coming on the course will be purchasing their own HPC system, so we haven't really covered that in any detail. If people do have questions about that side of benchmarking and acceptance testing, then I'm happy to try and answer them, but that is not the main focus of this course. The other thing I wanted to point out before we move on to the terminology is that it's not just the software package itself you're benchmarking, it's the combination of the software package and the input data, right? Because the scaling of the performance of a package does depend on what sort of input case it's treating. Throughout this course, and I'm going to try and be, I may make mistakes at doing this, but I'm going to try and refer to the two of them together as the application. So think of the application as the program you're running plus the input data set you're using. Okay. And that's a critical thing. Just because your software scales for one input case doesn't mean it's going to scale or its performance is going to be have the same properties for another case. Now, with a bit of experience, you can obviously extrapolate, depending on the size of the input deck and the types of algorithms it's using, the type of modeling it's doing. You can start to get a feel for how you might extrapolate those two. But that's really no substitute for actually measuring things. So a couple of final things before we get into running things. There's some terminology and some practical considerations or advice. So in terminology, we're going to use a number of different terms and concepts throughout the discussion on benchmarking. So I'm going to define them here so we're on the same page. So timings are the measured timing for the application you're benchmarking. These can be the full runtime of the application or timings for part of the runtime. For example, it's often common to see with things that are time stepping, you see time per iteration, or for quantum chemistry programs, you might see time per SCF, surface consistent field cycle. Okay, the performance is a measure of how well an application is running, and this is always measured as a rate. The actual unit performance depends on the application, but some common examples you see out there are nanoseconds a day, which is often used in, for example, biomolecular simulation. Iterations per second, again for some sort of time stepping thing. Simulated years per day for a climate model. SCF cycles per second. The actual measure you choose to make and you're going to base your decisions on is known as the performance metric. What is SCF? Sorry, SCF is self-consistent field. So within quantum chemistry calculations, each cycle in a geometry optimization is a self-consistent field cycle. It's like a single point energy calculation. Then there's baseline performance. So almost all benchmarking uses some sort of baseline performance to measure performance improvements against. So in HPC benchmarking, this is usually the performance on the smallest number of nodes possible to run your application on. In our case, for the simple example we're going to use throughout this course, actually we can run on a single core and use that as our baseline, which is sometimes thought of as the ideal baseline in HPC benchmarking, but it's often not possible because either that calculation will take too long to complete on a single core, or there isn't enough memory available with a single core run to be able to treat the problem. So usually use the minimum one that's possible within the constraints of runtime and memory. Scaling, which is the measure of how the performance changes as the number of core nodes or cores is increased, and it's usually measured relative to the baseline performance. There's also the related concept of perfect scaling, which is the performance you'd expect if there were no parallel overheads in the calculation. Basically, if you double the number of cores or nodes, then the performance from your baseline, then the performance should be twice as good. That would be perfect scaling, but that's not true in many cases. And finally, parallel efficiency, which is the ratio of the measured scaling to perfect scaling. So how efficient is it compared to what the perfect scaling should be so if it should go twice as fast, but it's not, then it may only have, say, 50% parallel efficiency. And there's a thought exercise here which you may want to do at some point, is think about if you're using HPC applications, what are the timings and performance metrics that might be interesting. Now, you may think that it's simple, right? You just use the whole calculation, but actually, for benchmarking cases, you generally want something that runs reasonably quick. It's because you're going to run multiple copies of it and you don't want to waste lots of resources. So say you're doing something that has iterations, and in the normal use case, it might do 1 million iterations and run for 24 hours. Then what you probably want to do is reduce the number of iterations drastically, say to 1,000. Now, the runtime is not important there, but the time per iteration can give you an indication of how long it would take to run for example, a 1,000,000 step run rather than a 1,000 step run. And you could use the same information to be able to understand the performance without having to do the full run. Okay, so thinking about what the best way to do that is within the constraints of being able to have something that runs reasonably quickly and doesn't use lots of resources is ideal. There are some applications where it's not possible to restrict the runtime very much, and then benchmarking can become a bit more of a chore because things have to run for a long time. So in terms of practical considerations, I think I mentioned this before with in terms of understanding your workflow. One of the key things you want to do is plan what you're going to do. What are you planning to measure and why? Are you going to look at what the most efficient number of nodes is to use? You want to understand what's the best performing algorithm that still gives you the right answer, or the best performing parameters in your application, but that still give you the right answer. Is it all of those things? If you're varying multiple parameters at once, it can be quite difficult to interpret the data. So ideally you'd vary one at a time and look at things along particular axes, because interpreting multi-dimensional data and it can become quite challenging quite quickly. There's potentially a lot of parameters you can vary. So understanding why and which parameters is a key thing. Benchmark performance generally should be measured multiple times to assess variability. So rather than just doing one benchmark run, typically people might do 3 or even more. 3 is usually considered the minimum, but more is better if possible. It depends how much resource it takes to run your benchmark case and how much that's going to cost you and what that means in terms of the resource you have available. And we're just going to discuss later in the course how you combine those multiple runs to produce a single value that you can use to make decisions on later in the course. Think about how you capture all the relevant information, because there's nothing more painful. I know, I've been there, of running lots of benchmark stuff and then realizing you didn't capture all the information you wanted when you ran them that time, so you have to go and do it all again. Okay, so put a bit of careful planning. That's one that's bitten me in the past, is you don't have access to all the data you need to do. And not most applications that run on HPC systems do not capture all that data, so you may need to add some additional things to your job submission or your scripts that you're using to capture the data. And we'll talk again about this later in the course and how automation can help you here. And organizing your output data so you know which output corresponds to which ones in your benchmark set. And we'll see examples of how to do that. But another thing you can do, which sometimes proves useful, is to include, for example, the job ID in the name of the output files, as well as the other things we're going to look at later. So what we're going to do here Yeah. Okay. So Georgia, having some sort of expected performance is useful. You may not have that for the case you're running it, and that's one of the reasons to run the baseline. But yes, if you've got some idea of what it should look like before then you can understand whether actually your runs are working as you expect or not. Okay. So we're going to use this. We've got a little training program on Archer 2, a little program that sharpens an image, takes a fuzzy image and turns it into a sharp image. And it's been parallelized in various ways and various times over various courses. The one we're going to use is an MPI parallelized version for this exercise. We're going to use this simple example HPC application to run some benchmarks with extract timings, compute performance metrics, and then after in this part we're going to do the collection of the data, and in the next sections we'll look at analyzing the data. So make sure you're logged into Archer 2. It's the first thing to do here, and because we're going to work alongside this, do this together as we go along. Okay. So what we're going to do here is explore how the performance of this image sharpening program varies with the number of MPI processes for the same input data. So we're going to have fixed size input data, which is an image of some size. We're going to run it through the sharpening program and look at how long that takes. Okay, and then measure that for various different core counts, and then we're going to look at that data and analyze it. So I'm logged into Archer 2 here already. My home directory is empty. Okay, so there's no data here or anything like that. The first thing I'm going to do is load the module that gives me access to the image sharpening program. So that's it, module load training/sharpen. And what that's done, we can use module list to show what modules are available, is added this extra module here, which gives me access to data and programs from this image sharpening. The next thing we're going to do is we're going to move to our work directory. If you remember back at before the break, I said that only the work directory is visible on the compute nodes, and we're going to be running on the compute nodes here. So all the data and all the output and all the things we're going to do need to be on the work file system. If you also remember, the work file system has the same structure as the home file system, but with just work at the front instead. So we can use our prompt here. So I can, for example, I can create the working directory, which is my home directory, and you can see it's got this structure. So I'm going to have /work at the start, and then the rest of it is going to be the same. So I'm just going to copy and paste it like that. Oh, but do you know what I've done? I've forgotten the CD command at the start. So I'm going to change directory to my work directory. Okay. This does have some data in it, but only because I was running some tests yesterday to make sure that everything was working as expected, and that I had example data sets in case things went wrong during the course. So your work directory is probably going to be empty. Mine's got these extra directories in from when I was testing yesterday. Okay. And then the next thing we're going to do, or actually the next thing we're going to make a directory to hold our initial benchmark, to do our benchmarking work and move into it. So let's do that. So mkdir sharpen bench, like that. Okay. And finally, in terms of setup, I'm going to copy across the basic, the input data, which is the fuzzy image, which is stored at this location. Sharpen input was set by the module that we loaded that just gives a location of the input data that we'll need to run these calculations. So I'm just going to copy that across. Again, I'm going to copy and paste my command. And what that should show us is that we've copied across this fuzzy PGM. You can have a look at how big it is. It's not a very big image at all. It's only 1.7 megabytes. Okay, so can I ask everybody to get to that stage where they've got a directory with the input data in? I'm going to put up a poll again and let people say whether they're there or not. And we can, if people are struggling, please let us know, and we can help out. Yes, so you can also create a link, so you can CD from your home directory. You have to be careful when you're using job submission scripts and submitting things that you don't use the link path rather than the real path to get into your work directory. The other thing I do sometimes, I can show you if I go back home, I can edit my /rc file, which is the file that's run every time it starts up, and I can set an environment variable that points to my work directory. And because that's sourced every time I log in, this environment variable should always be available for me. So I could log out and log back in again to source the /rc, but to get that available, or I could just use the source command to make it available now, and then I should be able to see cd $work, hopefully. Yeah, and that takes me to our work directory. And then you have to worry about the link thing, getting that wrong. Okay, so I'll just make sure that we've got everybody up to the stage of getting the directory. And having the data there. As I said, if people have questions, please feel free to interrupt or ask anything. There will be these pauses as well. Make sure that everybody's at the same stage. And they can often be useful for if people have side questions or other things they want to know. So I think there's a couple of people who haven't quite got there yet. If you're stuck and need help, please pop your hand up or pop something in the chat, and either George or myself can come and help you out. Otherwise, I'll just give it one more minute. See if people are there. I'm always conscious also in online sessions, it's quite hard to tell if people have just been called away from their terminal or not for a moment. So they might not actually be able to respond. Okay, as almost everybody's there, I'm going to kill that poll for now, and we'll move on. If any of the people who haven't answered yes are there and need help, then please let us know. If you're just catching up, then don't worry too much. We can always skip back if you miss something and help you out there. So the first thing we're going to do is get the baseline performance. So this is where we're going to compare all our the baseline timings and performance. So this is where we're going to start. For this very small example, we're going to use a single core of a compute node to get our baseline. As I mentioned before, that's not generally possible for real parallel applications, because either the memory requirements aren't large, you don't have enough access to enough memory with a single core, or you can't fit a run on a single core within a reasonable runtime. Anyway, but best practice is to use the smallest size that you feasibly can for your baseline. But in reality, doing the sort of quick and dirty benchmarking when you first get onto a system, then just picking something and then doing the half and twice as many is as good an approach as any to start your understanding. So these are, although these are ideals and good guidance, it's better to do something and not completely follow all the exact guidance than to do nothing at all and just go ahead and maybe use things that are inefficient. So sorry, excuse me. So the way we run on a compute node without having to write a job submission script. Yes, the other editors are available if you want to use them. But the way you run on a compute node without having to write a job submission script is to use the srun command directly. Now, it's pretty complicated and horrible, this command, because it takes a lot of options. So I'm just going to step through it and show you and just mention briefly what each of these options are, just so people, so there's no sort of mystique with them. The partition tells us what type of compute node you want to use. On Archer 2, there's only one at the moment, so it's standard, and it always will be. It always will be during this course. The same for the QoS. The QoS is like the queue. It sets the limits on like runtime, the maximum number of nodes you can use and things like that. So think of it as a queue if you want on the system. As mentioned before, we have a reservation, so we have nodes just waiting for people to run on them for this course to give you instantaneous turnaround. So that's specifying the reservation we're using for this account. The account is what budget you charge to. In our case, it's the same as the project ID you signed up for, which is TA036. These next two options, the hint, no multi-thread, and distribution block, tell Slurm how to pack the processes onto the compute node. This essentially means these two options actually tell it. The hint no multi-thread tells it to use physical cores only. You may have heard of with Intel CPUs something called hyperthreading, where each core can host multiple actual processes. And usually there's two processes per physical core. So there's twice the number of logical cores as there are physical cores. The same is true on AMD systems. This is telling Slurm that we only want to use the physical cores. We don't want to use the logical cores. So we don't want to oversubscribe the cores. Typically in HPC, you usually want to stick with physical cores only. There are a few cases where using logical cores give you a little bit more performance. So using twice the number of processes per node, but it's not generally the case. And the distribution block tells it how to pack them onto the node. So that this option basically means fill up from the start of the node. So sequentially, so process 0 will go on core 0, process 1 on core 1, and so on and so forth until the number of physical cores. Then we say we want one compute node. That's fine. And we want to run one task per node. That is one MPI process per node. So that uses a single core on the node. We specify runtime. This is 10 minutes. It's not going to take 10 minutes. And then the name of the program we want to run. In this case, it's called sharpen-mpi.x. That's made available through the module you loaded. And then we're going to redirect the output into a file. And in this case, it's going to be sharpen. Because we're varying the number of cores, we want to capture the number of cores we're using in the file name, just to help us keep track. And then as 001, you'll see why that's in there, because we're going to do multiple runs at each case. So there was a question there I saw about the number of physical cores. Okay, so sorry, I'll get to yours in a moment. So Archer nodes do have 64 physical cores. No, they have 128 physical cores. There's 64 physical cores per processor, and there's 2 processors on a node. So in terms of logical cores, there's 256 logical cores because you can have two. You can have 2 processes per physical core if you really want. JG, is that QoS standard the only choice? No, it isn't. There are other QoSs on the system. So we have a large scale for people who want to use a large number of nodes on the system. So if you're using more than, I think, 256 nodes, then you have to use the large scale QoS, which restricts your runtime and the number of jobs you can have queued so that one person can't dominate the system. There's also a long QoS that allows you to run for 48 hours maximum wall time rather than 24, sorry. And there's also a short QoS if you need to have quick turnaround. Now, the only thing I'd say, this command works if you're using an account that you signed up for through the course project. If you're using an existing Archer 2 account, I will paste the command. What you end up doing is replacing some of the options in that command. So let me just go to the setup, and I'll construct. Okay, so what it says is, you need to place the reservation and the name of the course reservation and use your own account. So what I'll do is in the Etherpad, oops, I haven't typed in it for a while, it's disconnected me, but there we go, we're back in. I will put in the equivalent command that you would need if you were using your own just going to pop that in as well, and then I'll do some mangling to make it work. So that's the command we'd use if we're using our if we're using course accounts. Right, the standard one in the documentation. Let me put that back, sorry. And if you're using your another Archer 2 account, which some people might be, or one that you had already for a different project, then you're going to replace the QoS bit and the reservation bit with these two, and you need to replace the account with your account that you already have. Okay. I wouldn't worry about the amount of resource it's going to take, because these are such small jobs, it's going to be tiny. So let's get back to where we are. So here's this command. Let me try running this. So I'm just going to copy this and paste it into my terminal. And it takes a moment because it's got to be scheduled and then run. And then hopefully what you'll see is it's done two things. It's produced the output file where we redirect the output. That's good. And it's also produced a sharpened version of the image. If somebody's really, really keen to view I'm not going to go into how you view the images, the fuzzy and the sharpened one in this course, because it's not really interesting. And it takes a bit more setup. It takes a bit more complex setup. You have to have an X server and all sorts of things set up. If you have a program that can open PGMs, then you're welcome to download and look at them. There's nothing special about the images, but you should see that one's sharpened and one's fuzzy. Okay. Yeah, you can check it ran correctly. We're going to assume it's running correctly here, but the setup of image viewing is a bit involved. Now, so one thing you'll see is that that's a pain to type. Okay, that command. So what we're going to do is we're going to set up an alias that creates a command that takes most of the stuff that's going to stay the same and allows us just to vary the bits, the bits that we're interested in, which is essentially going to be number of nodes and the number of tasks per node, and maybe the output file name as well. Okay, I'm actually, although here in the example it doesn't build in the time, I'm going to take the time across as well, because the time is always going to be less than 10 minutes for any runs we do. So I'm going to take this across, and this alias command, okay. So I wanted to add in here minus time equals 0, 10, 0 here as well. So I didn't need to specify the time. So now instead of typing srun, I could type srun opt, and it will essentially do all that, and I can add other options on the end. So let's try that. So srun opt. This time I'm going to say nodes equals 1, and I'm going to take end tasks. Where is it? End tasks per node, I think. Yeah. Node equals 2. Sorry. is 1 as well. So I'm going to run another single core job. It's going to be my next iteration, and it's sharpen MPI X, and we're going to redirect it as we did before, but this time it's going to be the second run. So I'm going to update the run number to 2. Hopefully that'll work. Okay, so now I have 2 outputs for 2 separate runs of the baseline run. And as before, if you want this alias to persist to be available each time you log into Archer 2, if you've logged out and logged back in again, then add the alias command to the end of your bash RC file on Archer 2. So I'm going to do that because I'll forget to set it up again. That's a pain. So I'm going to edit my home.bash RC file, which already had that in, and I'm going to add this command to it as well. So it gets set automatically each time I log in. So we managed to run 2, and then we're going to run it one more time. So we've got 3 separate results. So remember I said that 3 is usually considered the minimum. So I'm just going to use the up arrow to skip back through my commands, do the same job again, but change a 3 to the end. And now we have 3 results, hopefully, from baseline runs on 1 core for each of these jobs. So I'm going to pop up the poll again just to check people are up to speed. So what I want everybody is that everybody's got to the stage of having the 3 sets of single core data ready to go for the next step. If you run into problems, have any questions, please ask or pop them in the chat. So as George said, what we need to do is check the output data to make sure it's correct and that we've got some results that we want. So that's what I've done here. So what we're doing is I've used cat just because the output data is quite small for this program. You may want to use something like less if it's a bit longer. You want to be able to scroll backwards, up and down it. But I just used cat here and looked at the data from the first of our runs from the baseline, and you can see that the code reports a few different things of interest to us. It tells us that it's running on 1 process, which is what we did. We were running on a single core. It was a single MPI process. The nature of the input file, the size of the input file in pixels. It tells us something about the algorithm it's using, particularly the size of the filter that it's using to do the sharpening. That read the file in. It starts the sharpening calculation. Gives us some information about where we're running. So this tells us that the rank, a rank is another name for an MPI process, is running on core 0 of this node. Each node in Archer 2 has a unique ID, and that's what that is. Writes some output data, and then it gives us 2 timings. When we discussed timings before, it gives us a calculation time, that's the smaller one, and the overall runtime. Okay, so the overall runtime covers everything that the application did, which is from startup through reading data, doing the calculation, writing out the data again, and then shut down and stopping. The calculation time just covers how long it took to do the actual sharpening calculation, so not including the overheads of startup and shutdown. Okay, so it's the actual pure calculation time. So based on these timings, we need to propose is the output defined in Shrinath asks, is the output defined in the program sharpen MPIs or some of the Archer runtime outputs? Okay, so in this case, the program is hard coded to read in input from a file called fuzzy.pgm and write out to a file called sharpen.pgm. So they're defined by the program. Okay, the output here that we're looking at, we told the program to output it there. So you can see we said use sharpen mpi.x, which is the name of the program, and then the chevron says redirect any output from the program into this file name. So this text we're looking at was redirected from standard out into that file name using the standard sort of bash chevron syntax. Okay, does that answer your question? Cool, great. So we've got two timings, so we can define two different performance metrics here. And so here, I talked about a performance metric is always a rate. Okay, so we need to define something that's a rate here. Now we don't have iterations, so it's not going to be iterations per second or something like that. We don't have cycles, so it's not going to be those sort of things. We could just define calculations per second, which would be, they're just the runtime, 1 over the runtime. That's always an option to you for a performance metric. So 1 over seconds to give you a rate. But in this case, we can do a bit better because we know the size of the image and we know how many pixels we have. Ideally, you want a performance metric that's independent of the size of the calculation. Something that's independent. So what we could do here is define pixels per second for these two bits. So how many pixels per second does the overall runtime match on to take, and how many pixels per second does the calculation time achieve? Okay. So what we could do there is we know the image size is this size. We know the calculation times this. So we could define a performance in pixels per second. Actually, it works out being megapixels per second because of the size of the image, and it gives us some units in the right sort of area, the right sort of size, and overall performance in megapixels per second. Okay, so for the example that's in the text here, where it was 2.882 and 3.182 for the timings in seconds, then the image size is 0.43428 megapixels. So and there's the calculation overall time. So the calculation performance is that size of pixels divided by the time, so it gives you 0.151 megapixels every second. Okay, and the overall performance is 0.136 megapixels per second for the example here. They'll be slightly different for the ones I have here, for the one I have here, because the timings are slightly different because there's some sort of natural variation in timings. Okay, so for each of these runs, you could calculate a rate and a performance metric in megapixels per second for the two timing values we have. But we have not just one run here, we have 3 runs. So we need to think about how we combine the timings or the performance we can calculate from those 3 runs into one value that we can use here, because working with multiple values, it makes it harder to draw conclusions. You really need one value to work with. But how we combine them depends on what we actually want to do with the data. So, for example, you want an idea of the worst case, which may be what you want if you're estimating how much resource you're going to need in the future for a project, or how much resource you're going to need to complete your research project. And because if you've got the worst case, then it should definitely be less than that. So in those cases, you want to take the worst performance of the largest timing of the relevant values. You want an amount of work you're likely to get through the current resources you have. In this case, you may want to take the mean of the timings and then calculate the performance metric from that. Okay, there is some, you do have to be careful when you're taking means. Generally, taking means of rates is not a very good thing to do. Numerically, it can lead to incorrect conclusions. So you're usually better to take the mean of the timing data and then do the conversion to a rate. If you only have rates available, because that's what's output by your application, then you can use the arithmetic mean instead of you can use the harmonic mean rather than the arithmetic mean to combine them with a bit more, and that's a more robust way to do things. But generally, the recommendation is you take the arithmetic mean of the timing data before you convert it to a rate. If you want to understand why and where the explanations and there's lots more information about how to present data from benchmark, then there's this a really good paper by Thomas Hoffler at CS from Switzerland, who went through all this and looked at actually what people actually do in practice and why it isn't ideal. If you want an idea of the best case scenario to compare performance of different HPC systems or parameter choices, say different core counts, then you want to likely want to take the best performance at each of your relevant values. Okay, and that's what we're going to do here, because what we're actually doing is we want to look at is, how does the performance vary with the number of MPI processes? So we'll typically take the best performance to do that. But also you might want an idea of performance variation, to understand, how robust is the performance I'm getting. In that case, you want to likely look at the difference between the best performance values, maybe a percentage of mean performance or some such thing. So you could take like the mean of the timings, calculate the mean performance, and then look at the spread. But in this case, so it's always worth understanding what you actually want from the data before you make a decision about how to combine data. But in this case, we're interested in the change in performance as we change the number of MPI processes. So we're going to use the minimum timing value from the multiple runs, as this corresponds to the maximum measured performance. We can look at this more convenient. We can look at this for all of the ones we've currently got using grep, which just search for a string. So we just search for the string time in our output files. So we do grep time. Oops. Star that out, which gives us all of our output files. And you can see here we've got 0, 1, that's our first run, 0, 2, our second run, 0, 3, our third run. Our lowest overall runtime is from the second run here. But the lowest overall calculation time is actually from the third run here. Okay, if I look at the seconds. Okay, so they're not always in the same place. The two values. Okay, so maybe you would have thought a priori they'd be in the same place. So to make the process of extracting time and performance data from these output files easier and to save time with everybody, so that nobody has to write lots of scripts, we have created a little Python program that will take multiple files and extract the data for you and output them as a table and as a CSV file. So included in that module that you loaded is this sharpen data.py program, and you just give it the extension of all your output files. So for example, I should be able to do sharpen, what was it? Sharpen data.py. Name right, and the extension on the end of the files is they're all .out files. So I'm going to add it out, and what that will do is it takes each of the files it finds, it computes the size in megapixels, gives the calculate all the calculation times, and gives all the overall run times as well. Okay, so that's a convenience thing to make it easier to read out the data and look at it. So now we've got our baseline data. Next, we want to calculate the data on how timing's performance varies the number of MPI processes we use for the calculation increases. So this is where you go off and do all the different runs. So what I want you to do now is run a set of calculations in the same way we've been running them here for the baseline one, but to do the same with the same input up to 2 full nodes, which is 256 cores. Make sure you keep the program outputs in a suitable set of output files you can use with the sharp.data.py program. If you use the naming convention we use for the baseline with the number of cores in the output file name and the run number here, and all call them .out, then you should have no problems. You could do it exactly the same way using interactive job submissions like we've been doing here. You could write a job script if you prefer, if you're happy and confident doing that. But use a variable number of cores up to the full set of 2 nodes. What I would recommend to avoid you having to do too many calculations is to just double the number of cores each time and do those runs. So you've got the ones on 1 core, so you could do 2 cores, 4 cores, 8 cores, 16, 32, 64, 128, and 256. Okay, and that should give you plenty of data to be able to look at the performance and analyze the performance in the next step of this. So there is a solution here. If you want to have a look at the solution to speed things up, you're welcome to do that, or you're welcome to have a go at doing it yourself without looking at the solution first. It's now 11:39, so what we'll do is I'll give you probably until, well, we'll see how people get on. I'll put up a poll to see where people are up to, but in the first instance I'll probably give you up to about midday to have a go at this, and hopefully get all the data you want. We may finish it before then. So have a go using what you've done already to try on keep doubling the number of cores. We want 3 runs at each core count. And there is a slight wrinkle when you go to 2 nodes. Hopefully you can guess what it is from the calculate from the commands we've been issuing. But I'll let you have a go at that. As always, any questions, any problems, please either shout out, put something in the chat, put your hand up. We can come and help you. But I'll give you about the 20 minutes to go and have a go at that and try and get your full data set, and then we'll look at where we are then once we've got that going. So James asking where are those programs, and how is it run without the Python command? It's all to do with the module. So it's all to do with the module you loaded. Okay, so you're right there. So if you can always issue the module module show command. Tells you what the module does. So if I do module show training.sharpen, okay, what that does is it prepends the path. So in this directory are actually all the things you've been using. There's some other things as well, but there's the sharpen.mpi program, and there's the sharpen data.py command as well. So by adding them to this path environment variable, it means you could just type the command and it should just work, because all commands and all programs are just files in Linux. And you can always find out where they are actually by using the which command. So which sharpen will give you the full path to it. And standard commands as well, even works with standard Linux commands, which ls. The ls is in user bin ls. Okay. In terms of the Python, the reason we don't need to say Python in it, because if I just a minute. The reason you don't need to say Python sharpen Python.py, not sharpen Python, sharpen data, because I can't type, is that at the top of the Python program, it has this line, this hashbang line here, which tells it that it's a Python-free program. So it means you don't have to do the Python and then the name of the script .bash. It has the caveat though that you have to make the script executable for it to be able to work. You have to set the executable bit in the permissions to make it work. I'm happy to discuss that more on making executable Python scripts if you want. Yeah, exactly. Chmod plus X, and then you can just execute it as long as it's got that hashbang at the top that tells it how to which interpreter to use for the contents of the script. So I like George in his old-fashioned bash with his backticks. So what George has typed there is a command to look in it without having to get the path, which is what I did there. In the olden days, he says, you could get the output from a command directly into another command using backticks in bash. So less which. It still works. Okay, so that takes the command of which sharpen that data.py, passes it into the less command or the more command, which is similar as George using. So it does the same thing. The more modern invocation from bash is to put in parenthesis and put a $. On the front. So $ parenthesis executes whatever command is in there and then passes it out. So that's the sort of more modern bash syntax, with the backticks are what it used to look like. So in order to not to give away the solution, at least straight away, because some people might be trying it without doing things, I'm just going to cheat and copy across the test data I generated yesterday rather into this directory rather than actually run all the commands. So I don't give the game away while people are still doing things. Okay, but that is midday. I know that there's not everybody has finished the exercise yet, and got the results they need. What I'd like to do is at least show you the solution. You can keep working if you want and talk through it a bit, and then we can decide. Then we can decide where we go from there. George, would you be able to help out with the Python errors while I do that?
Yep, I'll have a look.
Okay, I'm going to kill the poll for the moment so I can see what's going on here. Yeah. So what we there are different ways of doing it. Doing this. Yeah. The Python script isn't hugely robust. It doesn't check that the file isn't empty before doing stuff. Anyway, so there's different ways of doing this. You can try writing a batch script, though we don't really talk much about that. So unless you're confident that's what I did actually, which is really stupid and brute forcing maybe, but actually doesn't take that long, was I took the srun commands, which if I can find them, they were quite a long way back. Okay, so like this, and I just kept changing the output and then rerunning. So for example, for a two core one, I do change the name of the output file, change the task for node to 2, and rerun that way. And I just kept repeating this command and changing it. For the only slight wrinkle was the 256 core one, which, because there's a maximum of 128 tasks per node, you can't ask for 256 end tasks per node. But if you ask for 2 nodes each with 128, that gives you 256 in total. So 2 times 128 is 256. So you can run that, and hopefully it runs across 2 cores. And I just did. Yeah. So if you have some slim.out, or something like that, if you have some corrupt files, then the script's not going to work very well because it'll hit a problem with empty files. As I said, it's not the most robust script. It assumes that all of the .out files have valid output in them. So once I'd done those commands a lot, yes. Once I'd done those commands a lot, you can see I end up with a set of data that looks a bit like this. So there's the single core ones we had before here. And then I've got 3 2-core ones, 3 4-core ones somewhere, 3 8-core ones, 16, 64, 128, 256. And you can check they're valid without running the script by just, remember we used the grep time. And you'd hope that would show that the times there with all the different files. Okay. And then we can run our sharpen data Python script, which has just been proved to be could be better architected, and maybe that's a good feedback, is to take something to the script and improve it, and it should give us some sort of data set that looks like this. So I've got 3 copies of each of them. All of them have the same size of image. All of them have some sort of calculation time. All of them have some sort of overall calculation time. Okay, that's my full set of data. If you haven't managed to get that set of data, or you're struggling to get it and you want to, you can either keep on working to get the full set of data. That's fine too, while I'm talking about the next steps. Or you can also just steal my test data set. So if you did something like, I've put them in a shared location. So if you, I'll put this in the etherpad in case anybody wants it. So if you copy from work, TA 036 shared, what's it called? Sharpen bench test start dot out to dot. You'd get the full set of the example data that I did yesterday. I'll put this in the I'll put this command in the ether pad so that people have it there. Also, I haven't typed for a while, so it's going to do that. I can't type. So if you want to skip the step of generating them and have a go at that at your leisure in the future, or play around with leisure, what I should have said at the start, and I'll say now, is that these Archer 2 accounts don't go away at the end of the day. You get to keep these accounts probably for another 3 or 4 weeks after the course. So if you want to continue exploring benchmarking and chase up on the exercises, have another go, try some different approaches to the exercises, feel free to do that. The way the course is set up, you shouldn't really use the course accounts for running research or running calculations for the research. They're provided to help you with the training. But if you want to have a go at exercise and try different things related to the course, then that's no problem at all. You can keep playing around with Archer 2 and explore those sorts of things. No problem on the accounts. You'll get to keep them for a few weeks after the course, at least, if nothing else. So we've got a data set now with not a huge amount of data, but large enough that we need to think about how we aggregate it and aggregate the data. And as I said before, we talked about different ways to aggregate data. The one we're interested in here is picking out the maximum performance. That's the same as the minimum timing. So we're going to use a tool called VisiData to do this, that's installed on Archer 2. What VisiData does is it gives you essentially a spreadsheet-like interface within the terminal window. So you don't have to, if you wanted to use a spreadsheet, you don't have to download it to your local system and use something like Excel or Numbers or OpenOffice or something like that. You can work with it directly in the terminal, and it saves you you can do some sort of more interactive work with the data rather than having to write Python scripts or Bash scripts to aggregate data. So it can be quite useful for exploring data. It works quite well with large data sets as well. This data set's quite small for it, but because it's quite low overhead. So it may be a tool that you find useful in general. But we're going to use it here because it provides us a good way to do things interactively with the data without having to learn scripting and stuff like that as well to do things in the course. So to make this one available, we need to load a couple more modules. We need to load the Create Python module, gives us a more recent Python environment generally on the system, and then load the VisiData module. So I'm going to do that here. So module load Create Python, module load. Okay, and all they do is add various commands tools, libraries to your path, so you can use the VisiData tool. You access VisiData with the VD command. Now, if you ls and look at what the Sharpen Data.py program did, as well as providing this summary on the terminal of our data, it's also written a CSV file, a comma separated value. So if I look at benchmark runs, it's the same data that was printed to the terminal, just in CSV. Okay. And that's the data we're going to use with VisiData, because VisiData can read in CSVs very easily. So what we're going to do is run the command VD to start VisiData, and then give it the name of the CSV file that we're going to work on. So VD benchmark run the CSV. I should. Okay, and we get the data from VisiData. To get out of VisiData, you just type GQ. And that get from wherever you are in VisiData, that'll get you back out to the terminal. And it won't save anything you've done. You have to explicitly tell it to save the data. So it'll just leave the CSV file as is for that. So can I just make sure? I just want to make sure that everybody has a data set either copied across from the shared location or one they've generated themselves to work with. I'm going to put, I know there's loads of polls, but it's easier for me to get an overview of where people are. Check that we're at a reasonable stage. Okay, almost everybody said yes. So what I'm going to do is I'm going to go forward at the moment. There's a couple of people who haven't responded. If you're having problems, then George and I will stick around at the start of the lunch break, and we can make sure you're up to speed in the right sort of place to carry on with the work this afternoon. If you're struggling, so let me just skip on. So what I'd like everybody to do is get to the stage where they can load it. They can load their data set into VisiData, the CSV into VisiData, and hopefully end up with an image that looks something like this. Okay, and one of the things with VisiData is when it loads in CSV, it doesn't know what type of data is in each of the cells. It's not like Excel. Yeah, it's not like Excel. So it tries to automatically guess at the data type in your cells. It doesn't do that. You have to tell it data type, and for it to be able to do calculations and aggregation of data, it needs to know what type of data set is in cells. And the two data types we're going to be working with really here are going to be floating point data, so that's real numbers, and integer data. Okay, so whole numbers, and use the way it works is you highlight the you can use the arrow keys to move around here in the interface. So that's me moving left and right, and I can move up and down as well. But there's always, what you'll notice, there's always one of the columns highlighted. And the way you can set the data type for a column is highlight the right column and then type the instruction key. And to make things integer data, we use the hash key, and to make things floating point or real data, we use the percent key. So I'm going to use the hash key on the number of cores, and you can see they jump to the right, and the hash appears at the top. That tells me now that is recognized as integer data or whole numbers, and we use the percent key on the other columns and turn them into floating point, designate them as floating point or real numbers. Okay, so you can all do that too, hopefully. And now it knows the type of data in each of the columns, we can start to do useful things in terms of calculation. So hopefully your interface looks a little bit like that now. So what we're going to do now is we're going to take the timing columns, the calc and the overall columns, and we're going to use commands to tell VisiData how to aggregate the data. Okay, so if I go to the calc column and then hit the plus key, it gives me some options about how to aggregate my data. And, I can choose various things here. You remember we wanted the maximum performance, and that's the minimum timing. So I'm going to check. I'm going to just press return or enter to choose min. Yeah. If you see at the very bottom in the status bar, it now tells me that this column has an aggregator set of min. Okay. And I'm going to do the same for the overall column. So I'm going to hit plus again. Now that overall is highlighted. I'm going to press enter or return to select min. And you'll see at the bottom, again, the aggregator min appears there. Okay. Okay, well, Gigi, we'll look at that in a minute. I just want to make sure we get to this stage before we do the aggregation before lunch, and then we can chat about that then. Okay, great, thanks. So now we've set that we want to do the aggregation. We need to, yeah, you can try Control H, or you can look at the documentation online as well. If we can, we now need to tell it which column to use as the aggregation base, to where to look for the values that are the same. So make sure that cores is highlighted, because we're aggregating based on cores. So we want the minimum value, for example, from all 16 core runs and all 2 core runs and all 4 core runs and things like that. Okay, so you need to make sure that that column's highlighted, and then we use the Control F. We use Control F to do the calculation and do the aggregation. So I'm going to hit Control F now. Oh, and I've obviously done something completely wrong. Let me go back. Oops. Okay, I've done something completely wrong there. So I'm just going to quit out and do all the, and repeat the steps again. So GQ to quit. I'm going to start again. I'm going to make them hash. %, aggregator min. Aggregator min. Go back to the cause. Oh, it's Shift F. Sorry, it's because I pressed Control F rather than Shift F. Sorry, that was me being stupid. Shift F. Okay, so that does do the aggregation. How do you do undo? I'm going to check the documentation. Type U, capital U. Yep. Okay, there we go. So let's try that. That didn't work for me. So I have not had to do undo. What I typically do if something's gone horribly wrong is I just quit out and start again, because the commands are quite quick to type, as you saw me just do a minute ago. So my my advice probably is GQ and then repeat where you're at. Sorry. I will have a play around at lunchtime and try and find the right way to do that, because that is obviously something that we need to know, but I don't know how to do that off the top of my head. George.
Sorry, I'm looking at the documentation and it says you need to enable the undo feature, so it may be a bit of a an orthogonal thing to sort out.
Okay, fine.
For some reason, it's not enabled by default. Don't know. There must be a reason for that.
I guess that maybe if you're working on very large data sets, it uses a lot of memory to keep all the things
or maybe
in
memory. 1970 when this program was written, it was challenging to undo.
Okay, so we've got that. The final detail I think that people would like to see is probably that you'd expect this cause column to be in the right order, to be in ascending order. So we can do that by hitting the left square bracket. So I highlight the column I want to order by. Left square bracket does ascending order. You can see the little arrow appeared next to the column up there to show that that's been done. And finally, as I said at the start of this, VisiData doesn't save state by default. Okay, so if I quit out of VisiData, I'd lose all this work right now, which is good because the easy way to undo everything is just to quit out and start again. But it does mean that if you just quit out, you lose everything. So you can save. We want to save this. So we use Control S to save and give the file a different name. We're going to call this one benchmark_ag.csv. So I'm going to type Control S, and I'm going to change it to benchmark_ag.csv. Okay, VisiData automatically knows that CSV means exporters, comma, separated values. So I'll do that. And so it's saved one sheet. So now when I quit, GQ, you can see that I've, as well as the benchmark runs.csv, I've got benchmark ag.csv, which contains that aggregated data set we had. You can change the precision as well of the perfect. Thank you, George, for investigating that in parallel. Okay, so you can just add the -- undo equals true option when you launch VisiData, and then you can use the undo command. Great, thank you, George. That's really useful. So then you've got the aggregated data set. You could also change the precision that these things are set. These yes, capital U, I think is where I'd shift U. You could also change the precision, but that doesn't matter for what we're doing here. So we're just going to leave it as the default precision for the moment. Okay, so this is where we're going to start from in the afternoon session, is from this aggregated data set. Don't worry if you've not quite made it there. We can pick up at the start of the next session. I'll double check that everybody's got aggregated data set to work with. and if not, we can work with you to make sure you got to that point. But otherwise, I'm going to give people the maximum their hour lunch break, so it's just after 20 past. We'll restart at 20 past 1. I'm going to stick around for a wee while, for 10 minutes or so, if people have questions or want to ask other things. So please feel free to do that. But otherwise, we'll see you at 20 past 1, and then we'll pick up with the aggregated data set and actually do some plotting and capture the performance data and start to make some decisions about what's the right thing to do. Okay, for some reason that's so. Have you got the right, Paul? Have you? So feel free to leave. Sorry, I'm happy to answer. I'm going to keep answering questions here, but go and have your lunch, and we'll see you back here at 20 past 1. Paul, okay, so and that's when you've got the cause column highlighted. Okay, I've not seen that particular problem before, I have to say. So, and is it definitely set as integer values, so it knows that it has to sort them numerically? So you could try doing it on the before doing the aggregation. Does it just work on the one? So if I type it there, it does work for me. Yeah, sure enough. Yes, so when we're using Visidata, Python scripts, etc., they're being run on the login nodes. They are. So unless you put your Python script command in a job submission script or use srun to launch it, yes, they all run on the login nodes. These are quite very small things. Actually, the login nodes are set up in such a way that a single user shouldn't be able to really hurt other users. We use something called C groups to restrict the amount of resource that each user can use, so you shouldn't be able to overload the login nodes. So if you're able to do that and overload the login nodes, then that's generally our fault as running the service rather than your fault as a user. Yeah, the only things that run on there, the only things that run on a compute node are things that are prepended with an srun command, essentially, or are within a job submission script that's sent to the compute nodes with sbatch. So anything else runs on the login nodes. Yeah, James.
Hi, thanks. I was just wanting to ask quickly, just thought it'd be a bit easier over voice. What is the best way to automate the submission of lots of these jobs where you're just changing the nodes by small increments and changing the output file name?
Yeah. So, no, that's a good question because obviously it's a bit tedious changing things and resubmitting all the time and a bit manual. We will talk about that this afternoon. Exactly that. There's a session this afternoon on automation.
Oh, okay,
we'll
that's
cover
perfect.
how to do that. As long as you're happy to hang on. If you want to go and have a preview, the materials are all up there. Feel free to go and have a look. But there's a section called automation.
Okay, that sounds great. Thanks. And I
Yeah,
see
Adam,
has
please
something as
do.
well, so I might look at that as well.
Adam, feel free to. I mean, it'd be really interesting to see. It'd be interesting to see how you approach that problem as well. So please do feel free to. If you're happy to share it, please do share it in the Etherpad. That's what it's there for, is for people, for attendees to share useful information too.